is the second half of the atmosphere notes. We're picking up in the third column on the front side, about halfway down where it says solar energy. What heats up the Earth's atmosphere? The transfer of energy from the sun, either directly from the sun's rays or indirectly by the Earth's surface absorbing the sun's rays. What is radiation? Energy the Earth receives from the sun. The energy travels in the form of waves. We all know about radiation waves. The complete range of these wavelengths make up the electromagnetic spectrum. How much energy reaches Earth's surface? Anybody want to take a guess? It's a percentage. Hopefully you can guess that at least it's not going to be 100%. We don't get all the energy from the sun. We get 30% of the sun's rays reflected by the Earth, 20% are absorbed by the atmosphere, and then 50% is absorbed by Earth's surface. So, taking a look at the picture here, after you finish filling in the percentages for each thing, in your notes it says sketch the drawing that represents Earth's energy budget. That's this picture right here, and then it's actually on the next slide. It's a lot bigger. So here's that picture, again, a lot bigger. So it's just showing you from the sun, 100% obviously comes from the sun, but 30% of what that 100% is reflected by the atmosphere. 20% is absorbed into the atmosphere. Remember how we talked about the ozone layer absorbs the UV rays? And then down here on Earth, 50% of the sun's rays are left to be absorbed by the Earth. So 50, 20, and 30 all add up to that 100% that comes from the sun. Now the greenhouse effect. If you've ever been in a greenhouse before, it's very hot in a greenhouse because of all of the glass and how it's sealed. So this is related to how we think about the Earth as holding in the heat. The absorption of long wavelength infrared rays from the Earth's surface trap heat energy from the sun and prevent it from escaping back into space. As a result, the lower atmosphere becomes warmed. What do you think would add heat to the atmosphere to cause the average temperature to increase? And we've talked about this a little bit. A lot of automobile emissions, anything like that, when you burn things, a lot of the stuff that we talked about when we did non-renewable and renewable resources, the non-renewables put out all of those pollutions, which helps to insulate the Earth and keep the temperature hot. So a lot of human activities change the balance between the amount of solar energy trapped and the amount that escapes. The burning of fossil fuels increases the amount of carbon dioxide, which absorbs the infrared rays. So the more carbon dioxide we have from the burning of fossil fuels, which would be automobile exhaust and things like that, that helps to absorb the radiation, which again insulates the Earth and keeps us hotter. So take a look here. Notice the difference in the size between the sun and the Earth. Here's the sun, real big, and then there's the Earth, teeny tiny speck. And then when we go in and we talk about all the different planets, next unit in astronomy, we'll talk more obviously about the planets, but notice how much bigger the sun is in comparison to the Earth. Why do you think it's important to discuss the difference between the size of the sun and comparing to the Earth? Really, so we can talk about the variation in temperature. Radiation from the sun is going to heat up the Earth unevenly. Think about seasons when we talked about those. Why is the equator hotter than the poles? Well, taking a look at the picture here, which again, you get to make another drawing. You get to sketch the remainder of the drawing about insulation. So we've got the Earth. The most direct sunlight is going to hit the Earth right there at the equator. So imagine the sun is over here on the left side of the picture. The most direct sunlight hits right there at the equator. And then as you move away from the equator, you get the same amount of light, but because of how the Earth is shaped, that same amount of light spreads out over a bigger area. So it's actually getting less direct sunlight, which means it's not going to be able to heat up as much. That's why the poles are cooler and the equator is warmer. What determines how warm the atmosphere becomes in any region? The location, the elevation, and the bodies of water. So where is it located? Is it near the equator? Is it near the poles? The elevation, how high up is it? Remember how we talked about the higher up you go in the atmosphere, in the troposphere, the colder it is. And then how close this place is to bodies of water. Generally, if you're closer to water, you're going to hold temperature better. Whereas if you're in the middle of a continent, temperature is going to vary a lot easier. And then measuring temperature. The instrument used to measure temperature is called a thermometer. Hopefully we all know this. And thermometers make use of a liquid's ability to expand and contract. So think about what we've just talked about in oceanography. What happens to a liquid when the air temperature falls? It's going to get closer to becoming a solid, right? Because those molecules contract. And then as the molecules contract, that's how the liquid can form into a solid or form ice. Scientists draw lines on weather maps that connect places with the same temperature. These lines, which are similar to contour lines, are called isotherms. Iso meaning equal, therm meaning temperature. So why would isotherms shift? Probably because we're changing. So isotherms are going to shift because every day the temperature changes. That's basically what you need to know about that. So I'm going to show you a map here with some isotherms. Here we are. You take a look up at the top, it'll tell you based upon the color what the temperature is at any place at any given time. So you can kind of see, and again, just like the note said, they're very similar to contour lines in that they're going to connect points of equal temperature instead of elevation. The sun's energy is transferred by a couple of different things. Conduction, a type of energy transfer in which vibrating molecules pass heat along to other vibrating molecules by direct contact. So if you think about a stovetop, when you put a pot on the stove, the pot is touching the hot burner. So this is conduction because they're touching. Whereas convection, the movement of gases or liquids that are heated unevenly, which is going to make the hot air rise and the cool air sink, this is the same concept from inside the mantle of the earth, just like with the lava lamp. As the bubbles heat up, they rise. As the bubbles cool, they sink. The hot air exerts less pressure on the earth, and cool, dense air moves into low pressure regions, pushing the warm air out, because that cold air is more dense. So it pushes out and takes over where that warm air was. And then the general movement of cool air is towards regions of low pressure. Cool, low pressure. The unequal heating and pressure causes winds. So when you have equalization of the two, you're not going to have winds, but on windy days, that's when the heating and the pressure is not equal.